Hello everyone. In this video we will discuss the fundamental group of wedge of circles. Firstly we define wedge of circles. Suppose X is a Hausdorff space which is union of the subspaces S1, S2, Sn, and each Si is homeomorphic to the circle S1. Now let us assume that there is a point P of the space X such that for any two subspaces Si and Sj, they contain P as their only common point. So let us assume P belongs to X be such that Si intersection Sj, this is P. So P is the only common point in all of these Si's. Then this space X is called wedge of circles S1, S2 up to Sn. So let us take this example of wedge of circles. Say we have this circle with radius 1, then circle with radius 2, then circle with radius 3, and so on. So all these circles, they have just this point 0 as their common points. This is S1, this is S2, S3, and so on. So their union X, that will be called wedge of circles. Now, one thing we can note here that if the space X is wedge of the circles S1, S2, Sn, then each Si, because it is homeomorphic to the circle, so this is compact. Each Si is compact and therefore it is closed in X. Now in this example, as we are taking the S1 to be the circle with radius 1 and at center at point 10, S2 is the circle with radius 2 and center at 20, and so on. If we take Si to be the circle with the radius I and center at I0, then X can be embedded in a plane. And X is homeomorphic to basically S1 union S2 union S3 and so on. So now we will find out the fundamental group of wedge of circles. So we have this theorem. And the theorem states that if X is wedge of circles S1, S2, Sn, and P is the common point of all these circles. Then the fundamental group of X with respect to point P, this is a free group. Free group means it is a free product of cyclic groups. So now we will further prove that if Fi is a loop in space Si that represents a generator of the fundamental group of Si with respect to P, then all these loops F1, F2, Fn, they will represent a system of free generators. So in this case, firstly we will find out for the finite number of circles, and then we extend it to infinite number of. So let us prove this theorem. Now we will prove this theorem by induction on n. Now if n is equal to 1, the result is very obvious. Because if n is equal to 1, the space X will be just a circle, and we have proved that for a circle the fundamental group is set of integers, and that is a free group generated by one element, means it is a cyclic group. So for n is equal to 1, the result is obvious. So we will assume that the result is true for n minus 1. So we will prove it for n. Now we are supposing that X is a wedge of circles of S1, S2, Sn, and the common point is P. Now we choose a point Qi in each Si different from P. For each I. And we define Wi to be the space Si minus point Qi. And then we define two different spaces. One is U, which is S1 union W2 union up to Wn. And we take V to be W1 union S2, S3 union up to Sn. Then U intersection V will be, now because Wi is a subspace of Si, because we get Wi by removing one point Qi from Si. So what is the intersection of U and V? That will be just union of all the Wi's. Now all these three spaces U, V and U intersection V, they are path connected because they are unions of path connected spaces with one point in common. So they are path connected. So diagrammatically we can simply represent like this. Say this point is P. This is S1, S2, S3, S4 with common point P. Now if we remove, let us say this point Q1, Q2, this is S1, this is S2, and if we remove this point Q2, then it becomes W2. Similarly here we removed, let us say this point Q3, then the space becomes W3. So here we remove this point Q4 and the space becomes W4. So union of all these, that will be U. Similarly, our space V, that will be so this is point P. Now we remove this point Q1 from S1. So this is W1, S2, S3, S4. So this is our V space. So this is V, this is U. Then their intersection, that will be removing this point Q1, which is W1. Now removing Q2, this is W2. Removing Q3, this is W3. And removing Q4, this is W4. So this is the intersection of U and V. Now we can see in this diagram also that each space Wi, that is homeomorphic to open interval. Wi is homeomorphic to open interval. So just one point of this interval, that is the deformation retract. So we can assume that P is the deformation retract of Wi. And let us take this be the deformation retraction. If some space is deformation retract of its superspace, then we have a deformation retraction map from x cross I to x, such that f of x0 is an x, which is identity, and f of x1 that belongs to this subspace, which means it is equal to P. And when we take a point in the subspace here, means f of P T, that is just P. So this is the deformation retraction. For each I. Then all these maps Fi, they will define a map F from U intersection V cross I to U intersection V. Because we know U intersection V is just union of all the Wi's, and on all the spaces Wi cross I, we have a mapping Fi. So we take F to be a mapping from U intersection V cross I to U intersection V, defined by F is equal to Fi when it is restricted to Wi cross I. And if we define this mapping just as the extension of all the Fi's, so let this be extension of all Fi's, then it will be deformation retraction. And it will be deformation retraction of U intersection V onto point P. Actually, we have to prove this F is continuous to prove that it is a deformation retraction, and that will be by pasting lemma, because F restricted to F restricted to Wi cross I, that is equal to Fi, and each Fi is continuous mapping, and all the Wi cross I spaces, they are closed in U intersection V cross I, and U intersection V cross I, that is just union of all the Wi's cross I. So by pasting lemma, this F is also continuous. Now it follows that U intersection V, that is simply connected space. Because it has a deformation retraction onto just a single point. So it is a simply connected space, which means the fundamental group of X with respect to P, this is free product of the groups pi 1 UP and pi 1 VP relative to monomorphisms induced by inclusion map. Now similarly, we can prove that S1, this is a deformation retract of U, because U is basically S1 union W2, W3 up to Wn, and all these Wi's, they have deformation retract as P, and if we take S1 to be just S1 itself, then S1 union P and so on, that is simply S1. So S1 is a deformation retract of U. Similarly, S2 union S3 up to Sn, this is a deformation retraction of V. So from this we can say the fundamental group of U with respect to P, that is just equal to fundamental group of S1, and this is a circle. So pi 1 UP, this is isomorphic to additive group of integers, or we can say this is infinite cyclic group. And by the induction hypothesis, we have assumed that the result is true for n-1 circles. So since S2 union Sn, this is deformation retract of V. So pi 1 VP, this is a free group by our induction hypothesis, and having the loops F2, F3 up to Fn as a system of regenerators. So here we are saying that fundamental group of X with respect to P, this is free product of the groups pi 1 UP and pi 1 VP. Pi 1 UP is infinite cyclic group which is represented by the loop F1. In pi 1 VP, this is a free group with the system of generators F2, F3, Fn. So it means pi 1 XP is a free group with the F1, F2, F3, Fn as a system of regenerators. And this completes the proof of the theorem.